to be a bit careful about the arguments. Nevertheless, it doesn't make a huge amount of difference, and you can't get away with having a D which is too big just by appealing to quantum mechanics. But since I've been doing a bit of mathematics here, let me do a little bit more of a different kind. This is also a very fundamental piece of mathematics, particularly to quantum mechanics, so let me talk about that. In fact, what I want to talk about is complex numbers. In fact, this is the thing which I'm referring to as the vessel plane. That's because he thought of it first, whereas people tend to call it the Argon plane or the Gauss plane or various other, I don't know, the complex plane, I suppose you can call it. But I think it's just as well to give Vessel the credit, because he even thought of it before Gauss, and that's some achievement. Of course, Gauss was only about 10 at the time, but nevertheless, I suppose he hadn't thought of it when he was 10, but I think he would have claimed he had if he had, so I think that's a bit unlikely. Anyway, the idea is that you just take any two real numbers, A and B are real numbers, so that's this R thing here, and you have this quantity I, which is the square root of -1. There's no real number which is the square root of -1, but doesn't mean you can't think of one, you see. You just say, all right, let I be the square root of -1. That's the nice thing you can do if you're a mathematician. As long as it doesn't lead to an inconsistency, that's fine. But it's much better than that, because it's very useful mathematically. You can do things, you can solve not just the equation x squared equals -1, which is the sort of cheating, that's what you started with, but any equation, polynomial equation. I've just written down one fairly randomly here. This has no real solutions, but you can be absolutely sure it's got complex solutions. Now, there's Gauss actually did come in and do this one. That's something he first proved, that that's always the case. It does other things which are part of the sort of magic. There is a great deal of magic in complex numbers, which is, I think, when I learned about these things, struck me very much. And it seems to me they're a much more beautiful system of numbers than the real numbers, so-called real numbers. It's misleading. You think of real numbers as real, and you think of them as real, I suppose, because time is sort of real and space is sort of real. So we think, whereas we don't think that square root of -1 is real in the same kind of sense. But then as soon as quantum mechanics comes along, suddenly you see it's in some sense has as great a reality as all the other numbers. So it's an unfortunate name, if you like. The complex, well, it's slightly unfortunate too, because they're not really all that complex, but still, never mind. You can write this combination of a real number and a so-called imaginary number, that is a bad name, and produce these things which you can plot nicely in this vessel plane here. Now, I'll just give you an example of one of the magic things that comes up. You see, in mathematics, you often have series like this one here, which is an expansion of something like that, and you find that this series works beautifully as long as x isn't bigger than 1 or smaller than -1. And what's wrong with that? Because you draw the curve of this thing, and it's got nothing funny going at those places at all. It's a perfectly good curve, absolutely smooth. Why should your series suddenly decide to go wrong at those places? Well, complex numbers explain it, and the vessel plane explains it, because you find that there's always a circle within which things work. It might shrink to 0, but there's a circle which divides the series for which work and those that don't work, and they always stop working if something goes wrong with a formula, and something does indeed go wrong with a formula at I or -I. You see, if you put I or -I in here, you get 1 over 0, and that doesn't work. So you know that 1 over 0 is going to give you trouble. So you know there's a singularity, as it's called, here and here. And so the biggest circuit you could draw through those 2 points is the biggest radius for this convergence. So you see why it works. I don't want to go into that here, but it just shows that there are all sorts of things like that which illustrate something which is very remarkable. You can understand things about real numbers much better when you know about complex numbers. But that doesn't tell you that it's got anything to do with physics. And that's, to my mind, one of the most striking things about quantum mechanics, that suddenly you find a role for these amazing numbers, that they are fundamental to quantum mechanics. And then you find that they do other things too. These complex numbers, that's what that funny C is, the complex numbers play roles in many attempts at new basic physics, for example, in string theory. Now, I'll come to that shortly, but before I do, let me say something about quantum mechanics, because I brought that up first here. So let's say, what's the role of these numbers in quantum mechanics? So I have here a slide, which is my description of quantum mechanics. I used this slide in a talk that I gave in Denmark, and I've been invited for some strange reason by the Hans Christian Andersen Society to give a talk. And I thought, why on earth have they invited me to give a talk? And then I remembered that I'd written a book, I think Paul referred to this, The Emperor's New Mind, which was based on The Emperor's New Clothes, you see, so I was using that as... I thought I couldn't use that, the talk I was supposed to give, I couldn't very well use that one. So I had to use some other, had to think of some other Hans Christian Andersen story, and after some deliberation, it seemed to me that The Little Mermaid was a nice illustration of what I wanted to, the sorts of things I was interested in then, which had to do with the foundations of quantum mechanics. And you might say, what on earth has that got to do with quantum mechanics? Well, you see, it really has, because you notice the bottom half of the picture is under the sea, and the top half is out here, and the bottom half refers to the world of quantum mechanics, where everything is all entangled and incomprehensible, and the top half is full of separate things and we can sort of get used to and think we understand. And what's the mermaid doing? Well, she straddles the two, and she represents the ingredient which links these two worlds together, which is sometimes referred to as measurement. Quantum mechanics actually consists of two separate parts. And although quantum mechanics is an extremely beautiful theory mathematically, and in that respect it deserves attention just for that reason alone, nevertheless, as I said before, it doesn't make sense. Now, what do I mean when I say it doesn't make sense? Well, it consists of two parts, really. One is this thing I'm calling U, which is basically the Schrödinger equation. Well, I've got it all over here, so let me say it on this other side here.